Hello. You've probably noticed lots of news stories recently about potential signs of life on Mars. So, how excited should we be? Let's take a good close look and find out. I am desperate to see the discovery of life on another world. I'm sure it's going to happen someday. I'm sure it's out there, probably all over the place. But that's just a hunch. And in science, you have to work on what the evidence actually shows you. And sometimes that evidence can be difficult to interpret. And when the results get into the media, sometimes they can be exaggerated. So you have to be slightly sceptical when you're looking at a piece of work like this. So, let's be sceptical. Here's the paper itself. It was published in Nature, probably the most prestigious scientific journal on the planet, and it's got a huge long list of authors. And first thing you notice is that that title doesn't actually seem to say anything about life. That's because they're not claiming to have found life. What they're claiming to have found is evidence of chemical reactions that may be evidence of life. That's a little bit different. One thing I should point out immediately is that little word organic in the title. Organic does not mean life. What it means is, well, there's a couple of different variations on the definition, but any compounds which have carbon-carbon bonds or carbon bonded to some other element by covalent means. So basically, anything which has carbon-carbon, carbon-hydrogen, carbon-nitrogen, anything like that counts as organic chemistry. It doesn't require it to have been anything to do with something that was alive. And we get organic molecules all over the universe. We see them in interstellar gas clouds, for example. So having organic material there doesn't actually mean anything on its own, and that's not what they're claiming. The study is based on these things. Tiny little, up to a millimetre size, so pretty small, concretions, growths of minerals that occur in a particular centimetre thick bed in one particular block of rock in an ancient deltaic environment. So this was a delta some 3 billion years ago, and there's wonderful exposure of the sediments, of the interbedded volcanic rocks in places. It's a fascinating place, and this is why the Perseverance rover has been sent there, because it is exploring for any evidence that it might have been habitable at one point. And they have spent quite a lot of time and effort with various different instruments that the rover has to examine the chemistry of these little concretions, these little growths of crystals. And what they found is, in a nutshell, it's indicative of what we call redox reactions. This comes from the terms reduction and oxidation, which is basically chemical reactions involving the exchange of electrons. They found quite a wide spectrum of minerals here, but the critical ones are something with carbon in, so organic material of some sort, and then an iron phosphate that they believe is vivianite, and then an iron sulfide, which they think is greigite. It is very, very difficult to pin down exactly which mineral you're looking at, but they all tend to give you the same sort of implications, so that's probably not too much of a problem. And this is a very interesting suite of minerals, particularly in the arrangement of these minerals. The researchers have called the tiny black dots poppy seeds, and then these larger ones with a black edge and a pale centre, leopard spots. But it seems as though they started as these little black spots, and then this was a reaction boundary that moved outwards, leaving behind the paler central region. That central region is mainly dominated by iron sulfides, and the outer part, the black rim, has a lot more phosphate in it. So they are different compositions, and it's suggestive of a reaction that is gradually progressing outwards through the surrounding sediment. Everything in the chemistry is consistent with the organic matter in this bed being oxidized, and the other side of the equation being the reduction of the iron and so on to produce this phosphate rim. That all works fine, and we do see extremely similar phenomena today, or at least in the fossil record. These pale structures here are what are called reduction spots. These are in the Old Red Sandstone of Devonian age on Earth, where you have things like plant rootlets growing through mud in a floodplain, deltaic system, just like on Mars. And when the organic material in the rootlets is decayed, it is oxidized. And the corresponding part of that is that in order to oxidize the organic material, the bacteria doing the decaying are reducing the surrounding sediment. So the oxidized iron, which is giving it the red colour, is being reduced, and you end up with a pale spot around where the organic matter has been decayed. So when you see similar structures on Mars, the question is, what's causing that reaction? So life does a lot of chemical reactions, and this is one of the things that you look at when you see redox reactions in unexpected places. So you have to consider it as an option. But when you're talking about life on Mars, you have to first rule out, or try to rule out, inorganic options. So things which are caused by perfectly normal, non-living chemical reactions in the environment. And that's what this paper is trying to focus on. So, the reactions that they're talking about have been fairly well understood. They occur on Earth in various places, and we understand the conditions under which they tend to occur. And naturally, on Earth, they occur where there is either high temperature, by which we mean 150 Celsius plus, or there is a high acidity, so very low pH. And either of these can generate the conditions needed for these redox reactions to occur to form vivianite, greigite, and so on. So the question is, did those conditions actually apply in this deltaic system? Let's deal with the temperature first, because this is relatively more straightforward. On Earth, when you're looking at rocks that have been exposed to high temperature, it's normally because they've been buried in the middle of a huge great mountain range. Those mountain ranges are the result of plate tectonics, which Mars doesn't appear to have had for a very, very long time, if at all. There hasn't been any mountain building event which has buried these rocks. In order to have the internal heat of the planet raising the overall temperature to 150 degrees Celsius, you would have to have buried it quite a long way down, even in the distant past, and then to have stripped off the overlying layers by erosion. And there just isn't really any evidence that that has happened to any significant degree. The other aspect, though, is that there is a lot of volcanic activity on Mars, and certainly was at around 3 billion years ago, maybe much, much more recently. And there are volcanic and igneous rocks in the area where these samples were taken. Now, there aren't any lavas directly in contact with it, so we're not talking about direct heating in terms of a magma flow coming over the top and just cooking it. That's not what we're up to. However, there are indirect methods of heating. And the authors of this paper do note that the rocks in this area of the Bright Angel Formation, as they call them, are often fractured and veined. And veining is what happens when you have hot water percolating through rocks and depositing crystals within the cracks as they cool. Now, if you have a source of very hot water in the form of igneous intrusions nearby, then it is quite possible that the temperature surrounding some of these beds was significantly higher than we might imagine. Dealing with the question of pH, though, is much more tricky. The authors argue that if there had been low pH, highly acidic, oxidizing conditions, then you would expect to also see some other minerals that they haven't found, things like aluminium phosphates. Basing an argument on the absence of a mineral when we don't know the full geological history of the site is a little bit dubious, especially when there is abundant evidence for very acid conditions elsewhere on Mars at similar sorts of times. So, if any of you remember the blueberries, these little spherules that were found abundantly in Jezero Crater by the Opportunity rover, those were associated with a suite of minerals that were very thoroughly investigated. And one of the things that they found was jarosite. This is an iron mineral that forms only under conditions of extremely low pH aqueous environments, so very, very acidic. We have to remember that this is not Earth. Mars was a very different world, especially in those early years when it started out wet. It had oceans, it had rivers, we know this much, and then it lost them. And when you go from a world that has so much water on the surface to one in which the atmosphere is being lost gradually, the water is evaporating, you end up with a situation that we've never seen on Earth. We don't know precisely what would have been going on. Acidic rivers sound a bit extreme, but on the other hand, during these last phases of the wet period of Mars, there may well have been very strange conditions, including acid runoff. There's also something else that I don't like about the images that we have of these nodules. And that's the fact that they are so evenly and randomly distributed throughout this layer. This is a centimetre thick layer of mudstone, which takes a little while to deposit. Or it can be deposited very quickly. In either case, it doesn't make sense for these to be focused on concentrations of organic material. So, if this was a mudstone layer that was deposited as a sudden event, a flood depositing it in maybe a few hours, then what you would expect would be a concentration of organic material that is winnowed. So normally that would be towards the top, the organic remains being lighter than the surrounding mud. That's not what we see. These nodules are scattered evenly throughout the bed. Okay, so if it was deposited slowly, then you have variations in the depositional rate. You have variations in the flow speed of the water coming in and how much mud it's carrying. So what you would expect there would be layers in which there's a higher concentration of organic matter and therefore a higher concentration of these concretions, these little nodules. And we don't see that either. What we see is completely even distribution. And what that looks like to me, unfortunately, is a mudstone layer which has a high proportion of carbonaceous material within it, all the way through just as part of the sediment. And then you have an external chemical influence, such as inundation by acidic water, which then causes pervasive chemical reactions throughout the whole layer. Okay, so is it evidence for life? Well, that kind of depends. If these structures were caused by some sort of biological activity, then yes, what we're seeing is evidence of it. The problem is we don't know. At the moment, I don't think it's possible to rule out these alternative interpretations of the origins of these structures, particularly relating to acidity, but possibly also with hydrothermal, maybe acidic fluids percolating through these rocks after they were deposited. At the moment, to me, it looks like an abiological interpretation is much more plausible. And the authors have done an incredible job with teasing out the information that they've got, working out what the minerals are. It's just how you interpret that I'm not sold on yet. I wish I was, and it wouldn't surprise me if there was life there at this time and still is now, and that we've seen multiple lines of evidence, things like the methane in the atmosphere and so on. But is it proof? Nah, it really isn't. Not yet. What we need, as the authors themselves have said, is to get these samples back to Earth, analyse them properly, work out what the organic components are. And it may be that those organic components themselves will tell us straight away that there was life there. Or maybe it won't. We just don't know. We need more work. And it's very easy to get carried away by these exciting headlines. But it doesn't do us any good in the long run. We can get excited by them in the sense of this is more evidence pointing towards complex chemistry, and maybe, just maybe, that means life, and cute little scuttly things in the distance. But we also have to bear in mind that that probably isn't the case yet. One day, though. I do recommend really getting into this study, though. The paper is available completely free online. You can find the supporting online information. You can even find the review files, which is very instructive. This is where it goes to the peer review process. The manuscript is sent out to specialists in the field who make comments, it's revised, and eventually it's published or it's not. In this case, I would notice there were 3 reviewers in 2 rounds of review. Reviewers 2 and 3 were very supportive, and they recommended publication after their comments had been taken into account. All fine, that's how it works. Reviewer 1, however, raised much more serious concerns, particularly about the direction that the arguments were going in, the interpretation. They were very happy and congratulated the authors on the work that they'd done, but raised several problems, and felt that these hadn't been resolved after the revisions. So Reviewer 1 actually recommended rejection. The editors, on balance, obviously thought that they did want to publish this, but of course the editors are also trying to sell journals, dare I say it? So there is often a tendency for the most exciting looking papers to get published. Even within the academic system, there is, in these very high impact journals, a certain amount of bias towards the controversial, the groundbreaking, and also the eye-catching research. So it's possible that if this had been published in a lower impact journal, one of the more specialist journals that publishes much longer papers, it would have been a much more thorough job, and we would have had a much clearer idea of what the data are actually telling us. Sometimes it's good to treat the things in the high-impact papers with the big press releases with quite a large pinch of salt. Just saying. Well, there you have it. That is the take of a humble paleontologist on a breaking astrobiology news story. And if you thought that was interesting, if you liked having a different perspective, then by all means stick around. Please hit that subscribe button. Please also tap the like button if you enjoyed it, because it really does make a big difference, especially in a new channel like this when trying to get noticed and reach more people. In future I'll be covering all sorts of other paleontology news stories, exciting developments, and who knows what else. Actually, I've got some vague ideas. You'll find out soon enough. Oh well, ta-ra for now.